All right, so we're going to start off with problem one. Here we got some bad eggs. It says that these eggs are contaminated with salmonella and can cause food poisoning in consumers. That's bad. The large egg producer takes a simple random sample of 200 eggs from all the eggs shipped in one day. The laboratory reports that 9 of these eggs had salmonella contamination. Unknown to the producer, 3% of all eggs shipped had salmonella. So we have to identify the population, the parameter, the sample, and the statistic. Okay, so the population is is the group that we want to know information about. It includes everybody. It's the entire group that we want to know information about. So the population would be all of the eggs that are shipped in one day. All eggs shipped per day. The parameter is going to be your math or your statistic. No, hold on, your statistic, but it's going to be it's going to be your proportion, population proportion. Um, so when we're talking about parameter, we're talking about the population. So we're not going to use the like hat. So it's just going to be P. P will be our population proportion or our parameter, which will be 3% or 0.03. Um, the sample is just going to be the number of individuals that we had. And in this case, we had a simple random sample of 200 eggs. So our sample, we'd like to use lowercase n to represent our sample size, which is 200. And the statistic will be our sample proportion, p hat. So p, see a little tiny hat there? Cool. And that's going to be 9 out of those 200, which will give us, I believe, 0.04, 0.045. Yeah. All right, simple. All right, problem two, we got this that we have to refer to. So researchers in Norway analyzed data on the birth weights of 400,000 newborns. Wow, that's a lot of newborns over a 6-year period. The distribution of birth weights is approximately normal with a mean of 3,668 grams and a standard deviation of 511 grams. So let's first write this out. I'm going to put an N of the mean is mu 3,668. Sigma, our standard deviation, is 511. In this population, the range, which is the maximum value minus the minimum value of birth weights, is 3,417. And here we use Fathom software. And they took 500 simple random samples of size 5 and calculated the range. So all these dots represent values of the range from small samples of only size 5. So this is the key. You want to make sure you know how to read the graph in terms of what it actually represents. So problem 3 goes back to this, but right now it's problem 2. It's saying sketch a graph that displays the distribution of birth weights for this population. So we're only talking about the birth weights. So again, be careful not to confuse that with the range because sometimes just when you just because it talks about the range last, you may want to just start like graphing something in terms of the range, but we're just talking about the weights, which is just this. We're told it's normal, centered at 3,668, standard deviation to 511. So just draw like a bell curve. as best as you can. And technically, um, the inflection point is supposed to be one standard deviation away. So if you were to add 511 to 368 or 3,668, you would get this value here. So that would be 4179. We took that away. 3668, 3157. But you don't have to get worried about getting that technical here. They just want to make sure that you can understand that this is going to be a normal distribution. All right, sketch a possible graph of the distribution of birth weights for a simple random sample of size 5. This is another one where they just want to make sure you understand what they're talking about. So you're really just going to draw 5 dots at, any possible birth weights. So you could pick like, I don't know. We'll pick some dots like that. We'll say this one happens to be like 3,700. Maybe this is 3,900. Maybe this is 4,000. 36. Maybe you could say this is 3,450. Again, it could be any 5 values. Um, as long as it's reasonable. Don't put like 0. Don't put like a baby weighed 1 gram. They ain't no baby, or don't put like 1,000,000 grams. Um, any 5 values, but you want to make it kind of centered at 3,668. All right, let's get to another one. In the graph above, there's a dot at approximately 2750. Explain what this value means or what this value represents. So this is going to be in a sample. We picked five babies. 5 babies were drawn, and this is saying that the difference between the maximum weight and the smallest weight in those 5 babies was 2,750 grams. So that's all it's saying. All right, and then all right, problem 3 is the sample range an unbiased estimator of the population range. Give evidence to support your answer. It is not because so this is the key. This is the key idea you want to understand. If a statistic is unbiased, it's going to be centered at the true mean value. Um, so for example, like for example, like the birth weights had a mean of 3,668, and a sample that you would make would still be centered there. Would be the mean of a sample of birth weights would still be at around 3,668 grams because they're unbiased. But sample ranges have to be biased because the thing is that in order to get in order for a range to be centered, let me just draw a picture, or let me draw a picture down here. If this was a distribution of ranges, let's say sample ranges, and we're saying that it's unbiased, that means it has to be centered at 3,417. But it can't be centered at 3,417 because that means there would have to be ranges that are greater than 304 than 3,417. There have to be some ranges over here, which is impossible because the range is the maximum value minus the minimum value. The range can't get any bigger than 3,417. So it can't be centered there. So then um it's gonna be unbiased. I mean, it's gonna be biased. It's not gonna be good to use this to estimate the true range, which is why you see it like centered like around 1,000. Sample ra ranges, they usually will always throw like one multiple choice question on your exam, addressing that. So just keep that in mind. All right, in part B, explain how we could decrease the variability of the sampling distribution of the sample range. Just get bigger sample sizes, more samples, or samples, well, more samples too, but bigger sample sizes give you more information, give you more precise estimates. So you'll have less variability. All right, let's go to problem 4. Do you jog? Sometimes. The Gallup poll once asked a random sample of 1,540 adults, do you happen to jog? Suppose that the true proportion of all adults who jog is 0.15. What does it mean of the sampling distribution of p hat? Well, it's going to be 0.15 because it's going to be centered at the true mean. So let's write this like this. We would write this as mu sub p hat, which is equal to the true population proportion, which is 0.15. Find the standard deviation of the sampling distribution of p hat. Okay, so then you'll have an equation sheet, and on the equation sheet it will say that the sampling distribution the standard deviation of the sampling distribution of p hat will be equal to the square root of p times 1 minus p. So of 0.15 times 0.85 over n over 1540. And we should get 0.15 times. Very, very small number. 0.00, we'll round to 0.0091. The 10% condition is saying that you're taking no more than 10% of the population. So your sample size is no more than 10% of the population size. So if the sample size is 1540, then the population size, large N, has to at least be 15,400, which it is. Is the sampling distribution of p hat approximately normal? Okay, well, when you want to answer a question like this is where you're going to have to check the large counts or show that you verify the large counts condition. Large counts. And that's going to be where you're going to have n times p and n times 1 minus p have to at least be 10. And this ends up being 1540 times 0.15. 231. 231 is at least 10, so we're good there. And this plus whatever this is going to have to add up to 1540. But let's just do it just to verify that it actually does work. So 1309. So both of these are at least 10, so we're good. So yes. Yeah. Part D, find the probability that between 13% and 17% of a random sample of 1540 adults are joggers. Okay, so we got to find the probability that p hat is between 0.13 and 0.17. Not a problem. Here we can use our calculator. So we're visualizing this. We're looking at a distribution. It's approximately normal, centered at 0.15. Standard deviation of 0.0091. So we're trying to find the area from a little bit to the left of the mean to a little bit to the right of the mean. Busting out the calculator. Go to distribution, normal CDF. 0.13 is the lower bound. 0.17 is the upper bound. The syntax here is then to enter the mean. So 0.15, comma, followed by the standard deviation, which is 0.0091. If you have a more advanced one or newer version, um, then it'll be very easy to see because they'll just have like entries where you that'll state enter the lower bound, enter the upper bound. So these old school ones you gotta memorize them. But we should get about 97%. Yeah, that makes sense. That's correct. 0.97. There's about 97% probability that between 13 and 17% of 1,540 adults chosen at random are joggers. All right, problem 5. Bag check. Thousands of travelers pass through the airport in Guadalajara, Mexico each day. Before leaving the airport, each passenger must pass through the customs inspection area. Customs agents want to be sure that passengers do not bring illegal items into the country, but they do not have time to search every traveler's luggage. Instead, they require each person to press a button, either a red or a green bulb lights up. If the red light shows, the passenger will be searched. A green light means go ahead. Customs agents claim that the proportion of all travelers who will be stopped is 0.3 because the light has a 0.3 probability of showing red on any push. To test this claim, a concerned citizen watches a random sample. They watch a random sample of 100 travelers, push the buttons, and they only see 20 of them getting the red light. So they're suspicious. So what's the probability of this occurring? What's the probability of only getting 20 of the 100 travelers getting a red light if we assume that the true probability is 0.3? So let's figure that out. So we want to find the probability that you get a sample proportion of 0.2 or less. Our sample size was 100. So we have to calculate the standard deviation of this. So the standard deviation of the sampling distribution of p hat, when we're talking about samples of size 100, this will be equal to the square root of 0.3. Remember, it's p times 1 minus p over n. And again, it's in your formula sheet. So 0.3 times 0.7 over n. So 0.3 times. So about 0.0458. Okay, so then we're trying to figure out essentially the area to the left of 0.2 and then an approximately normal distribution where the mean is 0.3 and the standard deviation is 0.0458. So 0.2 would be there. So something like we want to find this area essentially. So again, we can use our calculator. Normal CDF, the lower bound will be like negative infinity because we're going to do all the way to the left. So negative, like a big number, comma, upper bound is 0.2, comma, mean is 0.3, comma, standard deviation is 0.0458. And hopefully I didn't make a mistake and bang. About 14.5%. No, about 1.4, no, not 4, 1.45%. Um, yeah, again and again, if you have the more advanced calculator and the newer version, it's easier to see the syntax. Now, based on this, do you believe the customs agent's claim? Hell no, man. This is 1.5%. They're probably lying. I mean, it's possible, but the probability is unlikely because it's, again, 1.5%. So we're going to say no. All right, just two more. What's their adult intelligence scale? Is WISE is a common IQ test for adults. The distribution of the scores for persons over 16 years old is approximately normal with a mean of 100 and standard deviation of 15. So mean of 100, standard deviation of 15. What's the probability that a randomly chosen individual has a WISE score of 105 or higher? The probability that their IQ, let's say X, is greater than or equal to 105. So again, we have an approximately normal distribution, mean of 100, standard deviation of 15. Trying to find the area to the right of 105. That's right, calculator time. Normal CDF, 105, comma, very big number, comma, the mean, 100, comma, the standard deviation, 15. That's about 37%, about 0.37. About 0.37 that a person chosen at random will have a IQ of 105 or higher. Part B, find the mean and standard deviation of the sampling distribution of the average Y score for a sample mean. So for a sample of size 60. So now we want to find the probability that X bar is greater than or equal to 105, where N is equal to 60. So if N is equal to 60, we got to calculate the standard deviation of the sampling distribution of X bar. This formula is equal to the standard deviation of the population over the square root of the sample size. Or in this case, this will be 15 over the square root of 60. About 1.94. Now the mean of this sampling distribution of X bar is going to be the same as the population mean, so it's still going to be 100. So we're trying to find the area, again, to the right of a normal distribution with mean 100, but this time the standard deviation is 1.94. So this one has less variability. So 105, so it's probably gonna be very, very low because 105 is already like 2.5 standard deviations away. So let's calculate this. Standard deviation or normal CDF, 105, comma, infinity, comma, mean is 100, and the standard deviation is 1.94-ish. And look, see what we do, we get less than 1%. We get like only about 0.5%. So it's super low. And again, that makes sense because if you have a group of 60, it's gonna be rare. It's gonna be very, very nearly, it's gonna be very, 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 very rare that their average IQ is gonna be more than 105. Um, would your answers in any of the parts A, B, or C be affected? The distribution of the scores in the adult population were distinctly non-normal. Only for well for the first one, just because when you pick one person, um the central limit theorem doesn't apply. When you remember the central limit theorem, when you have central CLT, when your sample size is greater than or equal to 30, then the distribution will be about normal. So we can use normal distributions when the sample size is at least 30. And we had sample sizes of 60. So we're good there. The first one wouldn't work. The first one, well, yeah, it would be affected. All right, last one, detecting gypsy moths, whatever that means. The gypsy moth is a serious threat to oak and aspen trees. A state agricultural department places traps throughout the state to detect the moths. Each month, a simple random sample of 50 traps is inspected. The number of moths in each trap is recorded, and the mean number of moths is calculated. Based on years of data, the distribution of moths is discrete and strongly skewed with a mean of zero point 0.5 and standard deviation of zero point 0.7. So mean of zero point 0.5 and the standard deviation of 0 point 0.7. Now it's saying to, I'll explain why it's reasonable to use a normal distribution. Oh, well, we kind of just went over that because um, the central limit theorem, um, as long as we have a sample size of at least 30, we're gonna be able to make calculations using a normal distribution. So we're good there. Estimate the probability that the mean number of moths in a sample of size 50 is greater than or equal to zero point 0.6. So the probability that the mean number of moths, so that X bar is greater than or equal to zero point 0.6, where when N is 50. So then the mean here will be zero point 0.5 because it's going to be equal to the population mean, and the standard deviation of the sampling distribution of X bar will be equal to the population standard deviation over the square root of N. So it'll be equal to 0.7 over the square root of 50. And actually I shouldn't have wrote for this one we just need to write that because we're not considering the sample size yet. These are the population parameters. So let's calculate this for this sample size. 0 0.7 divided by 0.099. Really? Yeah, 0.099, I guess. And then want to find the probability that um the sample mean is more than zero point 0.6. So let me just draw the distribution here. So centered at again 0.5. We want to find the error to the right of 0.6. So again, approximately normal Mean of 0.5, standard deviation of 0.099. So using our calculator again. Distribution, normal CDF, 0.6, comma, a billion. Lower bound, upper bound, mean, 0.5, comma, standard deviation, 0.099. 15.6%. So we'll get about 0.156. There's about 15.6% chance that we're gonna get um a, a zero point 0.6 number of moths in a sample of size 50. Um, Part C, yes, in the recent month, the mean number of moths in a simple random sample of size 50 was zero point 0.6. Based on this result, should the agricultural department be worried that the moth population is getting larger in their state? No, because there's like a 15% chance that this is happening. 15% ain't that crazy, come on. That's like one in what, seven? Yeah, it's not too crazy. So no, blah blah blah. Again, because this is reasonable to happen. Um, all right, so there we go. I hope that helps. I hope it wasn't too boring and I explained that well. Let me know if you have any questions in the comments section. And if you're finding this helpful, make sure you guys subscribe and let me know what video you guys want next. I know AP season's coming around the corner, so I'm willing to look at any videos or make any videos that you guys need. All right, thanks for watching. I'll see you guys next time.